Okay, and we're back at it again. So, continuing our discussion of Chapter 7, we are now going to actually use the Laplace transform to solve some differential equations. Alright, so as you can see from the title, we're going to talk about two things: inverse transforms and transforms of derivatives. Alright, so we're going to work that backwards actually. We're going to start with the transforms of derivatives, and that'll lead us naturally to the inverse transforms. Okay, good times. Alright, and of course, as we go into this, make sure you've got pen and paper with you, and feel free to pause the video whenever you want. I will also include some prompts for when you should pause. Okay, here we go. Alright, so we want to use Laplace transforms to solve diff EQs. So, naturally, I'm going to want to take the Laplace transform of the derivative of a function. Alright, if I'm going to use it to solve differential equations, I should probably know how the Laplace transform of a derivative will behave. Alright, so if we're going to look at the Laplace transform of the derivative of a function, that means I'm going to look at the integral from 0 to infinity of e to the negative st times the derivative of some function f to the integral with respect to dt. Alright, so how are we going to handle this one? Well, it's an improper integral, so I convert it over the limit like that. And now I'm faced with a definite integral from 0 to n of e to the negative st times the derivative of f. Alright, well, I do not have any fancy tricks today. We gotta integrate this by parts. And this is pretty natural for a candidate to do that, right? Because we know with an integration by parts, we want to pick a function to take the derivative of, and we want to take a function to integrate. E to the negative st's got a pretty great derivative with respect to t. So note what I did there, and note my dt. I'm being a good math person today, taking those derivatives accordingly, and including the dt when I do my integral. Obviously, I've got the derivative of f, so I'll make my dv be the derivative of f. Alright, so now we'll hit it with our uv minus the integral of v du. So that looks like this. So this integral by integration by parts, the limit is just going to hang around the outside. U times v, so I'll have my e to the negative st times f of t, evaluated from 0 to n. And then the definite integral from 0 to n of the v, the f of t times the du, the negative s e to the negative st dt. Alright, so if we go ahead and clean all of this up, it's going to look like this. Here I pulled out a negative s, the minus sign cancels out. Plug in an n, we get our e to the negative sn, f of n, and plug in a 0, we'll just get f of 0 minus being subtracted off there, evaluating the definite integral. Okay, so we have performed an integration by parts. And now we're going to go ahead and take a limit. Now there's a couple of things to notice about this particular limit. Alright, well first off, the negative f of 0, not going to care about the limit, there's no n. The term on the right here, the integral from 0 to n, that is just going to turn into the integral from 0 to infinity. And, oh, hey, note, that's just going to be the Laplace transform of f. Well, that's nice. What about this term? Well, we need to make decisions about what s needs to be in order for this to go to 0. And we got to assume some things about f, so that f of n does not overpower e to the negative s. So right here, this term, I want to go to 0, obviously, because I have e to a negative, and I would like that to go to 0. But at this point, there are some decisions that need to be made. Now, did not touch on the last video, but if you go ahead and look in your textbook, specifically in section 7.1, they talk about when does the Laplace transform of a function exist, and there's this idea of being of exponential order. Got it, third time's a charm. And that's just some technical details to ensure that the Laplace transform exists, and some other stuff there, and it comes into play here because, like I said, we're going to play a little fast and loose with the limits, because we're going to go ahead and say that we've chosen s and f so that this integral evaporates. So typically what we'd assume is that s is greater than 0, and that our function f is of exponential order, which means that it does not overpower exponentials. It gets defeated by exponentials when you take the limit. So ensuring that this goes to 0. Alright, and like I said, this piece right here we should recognize. It's the Laplace transform of f, so I now have the following Laplace transform. The Laplace transform of a derivative is s times the Laplace transform of f minus the function evaluated at 0. So let's stare at this for a moment and really digest what it's saying. It's telling me that I can remove a derivative. So I have the derivative of a function, and when I Laplace transform it, I can turn it into a Laplace transform of the original function. So let's say I had an equation that had derivatives in it. Well, if I Laplace transform it, I'll remove the derivatives. And even better, if it's a nice linear equation, as we know the Laplace transform is linear, then you're cooking. All right, so speaking of that, let's see this in action now. I now know what the Laplace transform of a derivative is, so let's go after an initial value problem. Right, I see this f of 0, so I should probably look at initial value problems. All right, so here is a first-order linear differential equation. Initial value problem. I'm told f of y of 0 is 1. Now, this particular differential equation, you already know how to solve, right? It's a linear first order. Find an integrating factor, work through the process, plug in the initial conditions, bing, bang, boom, done. Now we got Laplace transforms, and like we said, we want to use the Laplace transforms to solve differential equations. We're going to go after some more interesting ones later on, but we do want to verify that this new technique is robust enough to actually be able to solve diffy-q's we've already seen. So I am going to solve this differential equation, and I'm going to use a Laplace transform to do it. Okay, so what do? I'll start off by just applying the Laplace transform. Apply the Laplace transform both sides of the equation. Okay, now on the right, I've got 9t. I know the Laplace transform of t, 1 over s squared. I know it's linear, so I can factor that 9 out. So on the right-hand side, I'm going to pick up a 9 over s squared. On the left-hand side, what's going to happen? Well, Laplace transform is linear, so let's pull it apart appropriately. Right? We can pull apart the addition, and the scaling by 3 is going to go on for the right. Now, as I just showed you, the Laplace transform of the derivative of y will turn into s times the Laplace transform of y minus y evaluated at 0. Nice. So now, on the left-hand side, I have an equation that's got some stuff going on with it, but the primary thing to notice is that now the derivative of y is gone. There we go. The equation no longer has derivatives. Right? So note, we use the Laplace transform to remove the derivative. Remember, the Laplace transform is an integral defined function. The fact that that removes its derivatives, not too surprising. Alright, so let's clean some things up here then. Let's mind our p's and q's, because I want to solve for y, right? The whole point here is find me the function y, whose first derivative plus 3 times itself is equal to 9 times t. Further constrained by forcing that y of 0 is equal to 1. So we know that there's exactly one solution to this initial value problem. Alright, so here we're going to now want to get the Laplace transform of y by itself. So I added the y of 0 over. Note I haven't plugged it in yet. I'm just carrying that along, just so you see how it goes. And note I've got a 3 and a s times the Laplace transform of y, so I can factor out. Hey, s plus 3, y prime plus 3y. I wonder if that always happens, and is a good check. Make sure you did it right. Alright, well, we know what y of 0 is, it's 1. So let's point that out, and then let's finally solve for the Laplace transform of y. Okay, so what have we done? I have just demonstrated that a first-order initial value problem via the Laplace transform is turned into a new problem. The new problem is the inverse problem. Hence the title for today. So, any initial value problem, whether it was a first order, a second order, third, so on and so forth, any linear initial value problem, solving it turns into solving an inverse Laplace problem. So in other words, I want to find the function with respect to t that gives me the function with respect to s that I have. So before, we were taking functions and applying the transform to create new functions depending on the new variable s. Now we want to go in reverse. So given a function in terms of s, find the function f of t so that it Laplace transforms to f. Right, the same way that we would find an antiderivative. I have the aftermath of a derivative, figure out what got me here. So you get to the the crime scene, and you want to know, well, what happened here. So notation that we will use for this is, rather than writing Laplace transform of little f is capital F, we can write it as Laplace inverse transform of capital F is little f. Okay. Nice. And again, note the variable situation here. Okay. Nice. All right. Now, the good news is, since we spent so much time setting up a bunch of properties of the Laplace transform, I immediately know a bunch of things about the inverse Laplace transform. Right, so I want to solve differential equations, and as we've just demonstrated, that is the same as solving inverse Laplace problems. So how do you solve inverse Laplace problems? Well, let's look at some basic ones before we get a little fancy. Okay, so we know something about the Laplace transform. We know the Laplace transform of t to a non-negative integer power. We know the Laplace transform of e to the at. We know the Laplace transform of sine and cosine. So that then tells me that the inverse Laplaces satisfy these. So the inverse Laplace of 1 over s minus a gives me the e to the at, right? Just swap where the Laplace goes. And same thing for the other ones. And also note, the inverse Laplace inherits the linearity that the Laplace transform had. So I can pull scalars in and out, and I can inverse Laplace over summations the way I would want to. All right, so the slide we ended on last time, now we've done it in reverse, and this is kind of the building block for things. So in the same way that kind of Laplace transforms themselves were this like brute force sort of thing, inverse Laplace is a little bit more finesse. So in the same way that taking the derivative of a function is brute force, just compute the limit, integration requires you to be a little creative. Inverse Laplace also requires you to be just a little smooth about how you do things. So, let's get some examples. So here we go. Let's say I want to get the inverse Laplace of 1 over 4s plus 1. Now, that almost looks like something I can handle. It'd be a lot better if it looked like 1 over s plus something. Because then, well, that looks a lot like the aftermath of Laplacing an exponential. Well, let's make it look like that by pulling out a fourth out of the bottom there. Now, as we just discussed, the inverse Laplace is linear, so I can totally get that 1/4 out of the party. And now I'm asked to look at the inverse Laplace of 1 over s plus 1/4. Well, I know the Laplace transform of e to the negative t over 4. The Laplace transform of that would be 1 over s minus negative 1/4. And thus, I have computed this inverse Laplace. Okay, so note a couple of things that went down here, right? So first of all, there was some scalar manipulation, and this is something you want to get pretty good at when it comes to inverse Laplace, because there's a lot of scalar tricks that you're going to have to be on the lookout for. And note what I did, I worked it to something that I knew, right? Because we know the Laplace transform of e to the negative t over 4, e to the negative 1/4 times t. I know what that's going to be, so I worked it backwards. Okay, let's try it again. All right, now we got something that almost looks like something I'd be happy with. I've got a 49 there, which is a number that should set off the alarm bells, because that's 7 squared. Now that 5, that's not going to help me with a 7 squared, so I pulled it out of the party. So that almost looks like a Laplace transform. Right, it's almost like the Laplace transform of sine of 7t. Not quite, I need to bring a 7 into the party, so I do the dirtiest math trick in the book and multiply by 1, here where I chose 1 to be 7 over 7. Alright, well that 1/7 is not helping me here, so let me get it out. Again, inverse Laplace is linear, just like how Laplace is linear. And now I've got 7 over s squared plus 7 squared. I know that's sine of 7t. There we go. Ah, nice. So these couple of inverse Laplace problems we've just done are not too difficult, right? Just remembering our Laplace transforms and being a little creative about our constants. Well, that's too easy. Alright, well, let's let our mind float back a couple of slides. This first order linear initial value problem, we cooked. We took the Laplace transform and it turned into this. So now, solving my differential equation turns into computing this inverse Laplace. Alright. Well, we now have what my solution to my diff EQ is, the function whose derivative plus 3 times itself equaling 9t, restricted to the constraint that at 0 it's 1. That function is the inverse Laplace of this summation. So I know the inverse Laplace is linear, so I know I'm just going to find the individual inverse Laplaces and add them up. Now, this one right here, we can hopefully immediately recognize that's e to the negative 3t. But this one over here, that doesn't look like anything we've taken the Laplace of. No, it does not. So what are we going to do with this one? Well, if you don't notice it, your brain does. I'm at the partial fractions this, aren't I? Yeah. Right, because if we look at this and think about it, we'd want to pull the 9 out, right? That might be your first inkling, your first thought there would be like, ooh, let's get that 9 out. But keep it there. It's going to help. Now, let your mind float back to calc 2. I have an s squared, s plus 3. That is factored as far as it goes, and it is irreducible. The s squared is going to introduce an s and an s squared. The s plus 3 is going to go on its own. These are all linear terms. That's a repeated linear term, so just constants a, b, and c in the top. Now, note that this breakdown is going to be good news for us, because I know what these Laplace transforms are going to be. Regardless of a, b, or c, whatever values they take, I know this is going to inverse Laplace to just a nice constant, right? 1 over s, the inverse Laplace of that would be 1. S squared, 1 over s squared, I know the inverse Laplace of that is t. And s plus 3, well, we already saw that was e to the negative 3t. So this breakdown, using partial fractions, is going to be the right move. All right. Oh, boy. So, what do we do? Well, there are, of course, 2 ways of attacking partial fractions. We naturally want to now cross-multiply. So multiply this s squared s plus 3 term to the other side. Convert it all over. Now, at this point, there are 2 methods, one of which is the correct way, and the other which is totally illegal. Now, the correct way would be to multiply everything out, line it all up, and then notice that, oh hey, I've got a polynomial on the right, a polynomial on the left, so the coefficients must match. Particularly a plus c must be 0, 3a plus b must be 0, and 3b must be 9. Now, a lot of people don't like doing partial fractions this way. They would rather start off with this equation and then plug in choice values for s, specifically s equals 0, s equals negative 3. But it's worth noting that that method, while that will work and give you the right answers for A, B, and C, a couple of issues with it. So first of all, those are precisely the values of s that we can't plug in, because those are going to be the divisions by 0. Now, note, this equation on its own right here doesn't care about that. So you can plug those values in and try to isolate values and solve for A, B, and C. But I do want to stress that that method for inverse Laplace almost always runs into issues of you need to be very creative about what values you pick, and also you need to usually pick complex numbers. We'll see that in a moment. I would recommend doing the multiply everything out and match coefficients method. I think it works a lot better. So specifically here, ooh, look at that. Those numbers came out very nice. I wonder if it's because somebody chose 9 there to make sure things would go well. No idea. Alright, well now we know A is -1, B is 3, and C is 1. Computing the inverse Laplace of 9 over s squared, s plus 3, turns into doing the inverse Laplace of these. Inverse Laplace, as we discussed, is linear, so it breaks up and pulls apart nicely. And these are inverse Laplaces we already know how to do. We know that 1 over s, the inverse Laplace of that is 1, 1 over s squared, the inverse Laplace of that is t, and 1 over s plus 3, the inverse Laplace of that is e to the negative 3t. So the solution to my first order linear differential equation with an initial condition y of 0 is 1 is as follows. Convert over to the inverse Laplace problem. This is an easy inverse Laplace. This one required us to get a little fancy with our partial fractions, but it all comes out, and there we go. -1 plus 3t plus 2 times e to the negative 3t. All right, and you can verify that that is indeed the right answer. In fact, use the integrating factor method that we learned all the way back in chapter 2, section 2.3, if I remember right. Maybe. I'll edit this video. No, I won't. I'm just doing these are one and done, man. I'm not even. Yeah, right. It's a very fun semester, right? Alright, well, that was fun. Let's have more fun. Alright, so now we saw how we can use Laplace transforms to solve differential equations. And you can keep going. We can, in fact, now tackle a second order problem. Now, if we were going to solve this using our previous techniques, what would we do? We would, of course, solve the associated homogeneous first. That would require us to find the auxiliary equation, get the roots of that, which are plus or minus 2i. That gives me my homogeneous solution. It would be a constant cosine of 2t plus a constant sine of 2t. Then we would need to find a particular solution. Because the right-hand side has nothing to do with the homogeneous solution, we'd probably do undetermined coefficients here, go for that process, and then get it all together and then plug in the initial conditions. So, non-trivial problem. Let me show you how you can use inverse Laplace and Laplace transforms to solve this differential equation. And in some sense, you're going to find that it's actually a lot smoother to use the Laplace transform. Alright, so you'll Laplace transform both sides of this. The right-hand side will be, note what the right-hand side is, s minus 1. It's e to the 1 times t. Rookie mistake to think that's 1 over s. I in no way did that while I was making these notes. You can't prove it. Alright, so the right-hand side, 10 over s minus 1 again. Laplace transform is linear, so the 10 goes along for the ride. Left-hand side now, Laplace transform is linear, so it breaks up like this. Now the question becomes, what do we do? So, the Laplace transform of the second derivative. The second derivative is the derivative of the first derivative. The Laplace transform of a derivative, we know, is s times the Laplace transform of the function who's getting derived, minus that function evaluated at 0. Nice. So, the second derivative is just the derivative of the first derivative. So I use our rule, and in fact you can extrapolate that rule to the second derivative. There's a formula for it, the third derivative, the fourth, so on and so forth. Your book has the formula if you are so interested. I don't think it's helpful to have it in your head, but it's there if you want it. Now, my problem has almost eliminated derivatives. I still have one more, so let me apply that rule again. So s times the Laplace transform of the function that's being derived, minus that function evaluated at 0. So note, we need this to be a true initial value problem. The value, I need to know what it is at 0. Right, so if these were different, if this was a boundary value problem, this technique would need a little massaging to help out, to make that work. But anyway, that's not here or there for today, so let's clean everything up now. So I know y prime of 0 is 0, so that's going to go away. I know that y of 0 is 1. And that is being multiplied by an s, so I know I'm going to pick up an s on the right-hand side. I have an s times an s, so I have an s squared Laplace transform of y. and a 4 Laplace transform of y. So, hey, s squared plus 4, second derivative of y plus 4y. Those look very similar, and hey, that's like the auxiliary equation or something. Oh, I wonder if that happens all the time. Okay, so my second order initial value problem I have now converted into an inverse Laplace problem. I just need to now find the inverse Laplace of that thing on the right hand side. And something you're going to notice while you do more and more of these problems is that you're always going to pick up a term that's usually immediately inverse Laplaceable. So this s over s squared plus 4, we already know what that is. That's cosine of 2t. Nice and easy. This other piece, though, well, we're going to have to partial fractions that. Sorry, they're back. And they want revenge. Okay, so the plus s over s squared plus 4, we already know what that's going to do. So let's focus on this 10, s minus 1 times s squared plus 4 term. And that's going to be a partial fractions. So we got some inverse Laplaces to do. So set up the partial fractions. The bottom is fully factored, and it's factored into irreducibles. Now, I do want to stress that technically we know that s squared plus 4 is reducible. It does factor in s minus 2i times s plus 2i. And if you're daring, if you are a daring individual, if you've got the metal, you can do it that way if you want to. You just got to be really good with your Euler's formula. But let's not do that. Let's do it this way. Because we know s squared plus 4, if there's an s on the top, I know that that will give me a cosine. And if there's an s squared plus 4 and a 2 in the top, I know I'll pick up sine. So let's leave it that way. We already know what those Laplace transforms are. So we'll treat this as a normal partial fractions, cross-multiply it over. Like I said, at this point, there are two potential methods. You can plug in choice values of s to try to solve for a, b, and c. And you quickly find that that's going to be a bit troublesome. If you really want to pull that move off, you're going to have to plug in complex numbers. So not recommended. It is possible, but the preferred method, the correct method, the absolutely legal method would be to multiply everything out, group your terms together. The right-hand side is a polynomial. The left-hand side is also a polynomial. The coefficients have to match. So I have to have that a plus b is 0. There is no s squared terms on the left. Negative b plus c has to be 0. There are no s terms on the left. And the constant term for a minus c, that needs to equal 10. Okay. Now we've got a nice linear system. The middle equation tells me that b is equal to c. The one on the left tells me that a is negative b. And using that information with the 4a minus c is equal to 10, quickly, nice and easily solved, tells me that a is 2, b is negative 2, and c is negative 2. Alright, so that one isn't too bad. So now when it comes to inverse Laplacing this piece right here, we know that it boils down to doing this inverse Laplace, so there's the partial fractions, but we can do one better and pull that apart into 3 distinct pieces, because as we know, the 1 over s minus 1, I know that will Laplace transform to e to the t. S over s squared plus 4, I know will Laplace transform to cosine. Note, I pulled the negative 2 out because I don't need that negative 2 to do the Laplace transform. Note here, I kept the negative 2 in. I kept the 2 and I pulled the minus sign out because I need the 2 to Laplace transform. Note, if somebody wasn't nice and picked nasty numbers here, you would have to do those little scalar tricks we talked about earlier on. But I made it easy on myself. And I know that the first term will give me my 2 e to the t, my second term giving me my negative 2 cosine 2t, and my third term here giving me my negative sine of 2t. And now we can solve our second order linear non-homogeneous initial value problem, constant coefficient by the way, because I know it's the same thing as this inverse Laplace. We just worked out the details on the left. That's going to be 2e to the t minus 2 cosine 2t minus sine of 2t. And as we discussed, the term on the right, the s over s squared plus 4, that's just cosine of 2t. And that cleans up like that. And hey, that solution sounds pretty legit, as we already discussed. If we were going to attack this with our previous methods, we'd solve the homogeneous first, then find a particular solution. The homogeneous we know had to be cosine of 2t and sine of 2t, so that lines up. And the right-hand side, we would have guessed a particular solution, a scalar multiple v to the t, and we see that that is indeed the case. Alright, so Laplace transforms can solve differential equations, and now we know how to do it. Alright, so what's up next for us? So we've learned the properties of the Laplace transform, so basic transforms, and we've now seen how they can be used to actually solve differential equations. So where are we going next week? Alright, well, the plan for the next set of videos, section 7.3 and 7.4, we'll talk about some more things that the Laplace transform satisfies. So we'll talk about some things to make computing Laplace transforms and inverse Laplace transforms a little bit easier. So there are some ways we can get around the partial fractions. We'll talk about those. We'll also talk about what happens when you take the Laplace transform of piecewise things and how to inverse Laplace that stuff, because as we just saw, if you want to solve a DE, you need to be able to Laplace transform and inverse Laplace. So we'll talk about that. And then we'll wrap everything up in 7.5 in a little bit here, where we'll get crazy with the Laplace transform. More on that later, but that is all for today. Thank you for joining me. Like, comment, and subscribe. And yeah, I don't have a Patreon, but if you want to give me money, I'd appreciate it. Okay, half my salary is your tuition. You don't need to pay me. You already do. Okay. All right, that's it for today.